This is Rust in Production, a podcast about companies who use Rust to shape the future of infrastructure. It's Matthias Endler from Corrode, and today's guest is Adam Hendel, founding engineer at Tembo. We talk about production-grade infrastructure on top of Postgres with Rust. Adam, thanks for joining us today. Can you introduce yourself and tell us about Tembo? What exactly are you building there?
Yeah, thanks for having me. I'm Adam Hendel. I am one of the first engineers hired into Tembo. And Tembo is a managed Postgres platform, where you can click a few buttons and get a managed Postgres database pretty quickly. Yeah, and on the Tembo platform, one of our main products is what we call stacks, and that's where you can get Postgres pre-configured for certain types of workloads for you with those same few clicks. So if you're doing OLAP or search or doing something with AI and you need embeddings, in that example, we have a vector DB stack that gives you everything you need to go build your application.
What is it about Rust companies and their love for Postgres? It seems like every other Rust startup I talk to is building on top of Postgres. What makes this 40-year-old database so appealing to modern developers?
I mean, I love Postgres because it just works. I learned to write SQL on Postgres. And earlier in my career, I was doing a lot of stuff in data science and machine learning, and I didn't know really what write looks like in terms of good SQL queries or efficient ways to build an application. And Postgres was just there, so I just abused the hell out of it, and it always just kept working for me, no matter what I threw at it. And over my career, I got better and then learned how to do things really way more efficiently. And then Postgres became to shine even more. So, for me, it's just super flexible, always been able to just work for me. Don't have to hassle too much with tuning it or anything. It just works.
Isn't Postgres already production ready out of the box? What exactly are you building on top that goes beyond just hosting it?
As you do get to having very specific types of workloads, and you want to start to make some trade-offs to really get all the juice you can out of Postgres, you have to start to make some decisions. And that's where you don't have to touch the C code, but you might have to touch some of the configuration. For example, there are certain configs in Postgres like shared buffers that kind of decides how much of your system's memory can you allocate to put the working set from your database into memory. So that's something that we can set dynamically for you. And then certain extensions that can really improve and change your experience with Postgres. Those can be quite a hassle to get installed. So we pre-install those into Postgres for you and kind of go through the process of, for specific types of workloads, what are the best extensions to make Postgres the best that it can be for that workload. So it's kind of configuration and getting the extensions installed and providing a really good experience around that.
So you're dealing with configuration, extensions, performance tuning. When you started building all of this, was Rust the obvious choice, or did you consider C, C++, or Python maybe as an alternative?
Well, since Postgres is written in C, that was definitely something that came up. The experience of building software in C is not, it's not super modern. So for somebody like me, I think the first programming language I learned outside of HTML and whatnot was R for statistical programming, and then Python. And in Python, you have stuff like the Python package index where you want to do something. Well, hey, there's a library for that. And you can just pull in that library and work on solving the specific problem that you're trying to solve. That kind of exists in C, but it's not at all quite as easy to just get up and running building stuff in C. So even though Postgres is written in C and it's super performant and very stable, it is hard to just come up on it and start to add functionality. But in Rust does have cargo and crates, and if you are trying to build software, you can get up and running pretty quickly with Rust and using, other libraries that are in crates.io and whatnot.
Okay, I get the C limitations, like no modern tooling, painful package management. But you mentioned coming from Python, which has great abstractions and developer experience. Why not use Python for this? Did you at least prototype in it before jumping to Rust?
Well, at the time that at Tembo that we were getting started building extensions, there was a framework that made it really easy to get up and running with Rust. That framework's called PGRX. Well, at the time it was just called PGX. They renamed to PGRX at some point. But to go from like nothing to a hello world example, it was like an hour or less to create an extension that, you write some function in Rust, turn that function into a SQL function that you could call. That was like super easy. So it was kind of, like we didn't have to, we were up and running really quickly. So we didn't really explore Python too seriously.
Okay, that's pretty impressive. So PGRX made it super easy to get started, but I don't really understand how Postgres extensions actually work. You write a Rust function, somehow becomes a SQL function. What's happening under the hood? Is there some kind of plugin manager? How does your Rust code actually talk to Postgres?
Yeah, so you can write functions in pure SQL. There's procedural languages like PGSQL that you can, kind of still just write, kind of SQL and easily create these functions. So there's an object that lives in Postgres, and it's a function that's an object in Postgres, and that function can kind of point to SQL code or one of the procedural languages, or it could point to a shared object. So now that shared object could be compiled in C or it could be compiled in Rust. So in the case of building extensions with PGRX, you have this function, and it really just points to a shared object that's the code that you wrote in Rust. So when you compile a PGRX extension, you might create some functions. There's more complicated things you can do than just functions. But like in this case of the function, there's some code that's like, hey, I'm creating a Postgres function, and that function is pointing to your Rust shared object.
But wait, if extensions are just functions pointing to shared objects, how do you handle state? Functions are supposed to be stateless, but any real application needs to manage state somehow. What happens when you need to maintain data across calls or coordinate between operations?
Yeah, so it does get complicated to manage state. I think the default, like when you call that function, everything is starting to happen within a transaction. So you can start to store state just in memory. Like as soon as you call that function, you imagine like you're going to read some data from a other table in Postgres, and you can pull that into memory and then go do whatever it is that you want to do, and ultimately, return some result set back to who's ever calling that function. So you could store it in memory, or you could store it in some intermediate tables back in Postgres. But in those cases, you'll be working through the Postgres SPI, and that's the server programming interface. So you have some tools available to you to kind of deal with your state there.
And the other thing that bothered me while you explained this, you're going through this SPI, this server programming interface, dealing with FFI boundaries. Don't you lose all the conveniences and ergonomics of Rust's type system? I mean, how would Postgres even know that a function is really available? All of Rust's advantages are in its type system and safety guarantees. Don't you lose all of that at the FFI interface?
In the memory space where your Rust code is written, you still have all of Rust features available to you. So, as you interact with FFI, you get all the FFI integrations. If you're using PGRX, PGRX abstracts that for you mostly. So you just write Rust code generally the same as you would if you're, writing a web application or, some script in Rust.
Okay, you convinced me. PGRS seems like the way to go if you want to start a new extension. But did you ever hit any limitations which might make you move away from PGRX, or is everything pretty much covered?
A lot of stuff is covered. There are some limitations, and I feel a little bad in what I'm about to say, because I wish I could have contributed back to PGRX. But some of those SPI, the server programming interface in PGRX, are just not fully optimized. So if you have like some SQL that you want to execute through the SPI from using PGRX, you have to data that kind of goes to and from Postgres through that SPI, you have to serialize and deserialize all of it, even if you're not really going to touch it. So there's a message queue project that we worked on called PGMQ. It was originally written in Rust using PGRX, and particularly for the batch operations where we would, send or read, 100 messages at a time. Those would get real slow because we would have to iterate over everything, every message, and just deserialize it and then reserialize it as we would, send it back to the user. But in those cases, like, there's not a ton of advantage to, just not be using just pure SQL for those cases.
Does this mean the code base is now mostly SQL with a nice Rust wrapper on top? You've kind of inverted the pattern. Instead of writing a pure Rust Postgres extension, now it's SQL with a nice wrapper around it, sort of. Like, what are the boundaries between SQL and Rust in that case?
So PGMQ, I can just tell a little bit of background about that project. So at Tembo, we needed a queue between our control plane and our data plane. Data plane is like where we spin up people's databases, and control plane is, back-end web applications. So we were building this queue on Postgres, and all of our tech was already in Rust. So we basically had a bunch of like SQL strings like written in Rust code, and that code would be duplicate across the control plane, and then the same service in the data plane would have like the same SQL statements for like sending messages and reading messages. And that was all Rust. So we first pulled it out into a crate and then installed the crate all the places that it needed to be. So it was all client side. And, since it was a crate, it was already kind of packaged up. We could turn the crate into a Postgres extension using PGRX it was like, I don't know, a couple hours worth of work to take that crate and use PGRX and create an extension out of it. So then in that case, like, there were all these shared objects for every function in Postgres, and, it was great. We had this extension, and we could ship that extension around to different Postgres instances and share it with the world, and, it was great. And then we started to run into those limitations where, it was really how we were using PGRX made some things slow. So we actually, was with the help of the community, and we even got some help from folks at Supabase to rewrite it from PGRX Rust into PL/PG SQL. And that was just for like the queue operations. And, there's still, we still want to use that extension at Tembo, and all our stuff is in Rust. And, tons of people around the world have their applications in Rust and want to use this extension too. So there's the Rust client library for it. And that is to like give you the idiomatic Rust experience for using PGMQ on Postgres.
It's a very nice pattern. You go from plain vanilla SQL, extract it into a separate crate, and make it a Postgres extension with PGRX. And I really like these code usability stories. I hear that a lot, and I really like that about Rust and being able to kind of move things out into separate crate. So that was the transition, if I understood correctly. But then you run into serialization issues, because when you try to get batches of messages over the wire, it's probably an O of n operation to go through each and every message and deserialize it with 30, and that can be slow. And eventually you want to go back a little bit and write parts of the more performant code in maybe a lower level abstraction, or maybe not use PGRX for that case, right?
Yeah, that's exactly it. We talked to the PGRX maintainers about what we were doing, and they're like, "Hey, what you're doing doesn't really need to be in PGRX. You're just executing SQL statements." And yeah, there are some limitations right now with the maturity of the API that PGRX had around just executing SQL statements. So it was kind of this should be SQL instead of in Rust.
But couldn't you have kept a hybrid approach? PGRX for most things, SQL for the performance critical parts. What made you abandon PGRX entirely?
We could have, but there's some additional gotchas with extensions in Postgres, and it's mostly around the portability of extensions. So if you have an extension in Postgres, extensions have the objects that we kind of talked about earlier, and they also have control files and migration files and all these other things. And for it to be an extension, those things have to be on the same host as Postgres. But let's say you're running on RDS, or you're running in Supabase or Google Cloud somewhere. If it's an extension, then you have to deal with all these additional things. But if it's just SQL, then you can just take that SQL with you and manage it however you want to.
From that perspective, it makes total sense. The PGMQ client caught my attention because unlike Nets or Kafka, it's just Postgres. So no need for new tech in your tech stack. But what impressed me the most was how Rust-like the API feels. How did you make a SQL-based queue feel so idiomatic to Rust developers?
Yeah. So, my opinion, and I didn't write all the client side code here. So we had some help from the community who, built some of these things. But the things that I care about in the client are establishing a connection pool to Postgres. And you can let the client do that for you, create a pool to Postgres, a connection pool. But maybe you're doing a bunch of other stuff in your application too. So we have the ability for you to create the pool yourself and provide the pool to the client and let PGMQ's client use your pool. And so in the client, with Rust, there's some generics typing that we could do with that to be how we execute the Postgres functions for the queue. We just take in certain, as long as the objects have certain traits implemented, we can execute that SQL. And if it's in a different language, I don't know if it'd be way more complex. But since we can just make these assumptions hey, pass in this thing, as long as it implements these traits, we're good to go.
You mentioned SQLx. Some people might not be familiar with it. What makes SQLx special for this kind of work?
Yeah, and in fact, the PGMQ client uses SQLx. So SQLx, I describe it as everything that I care about from an ORM, but it's not an ORM. All the great things and none of the bad. So SQLx, it does a lot of things, and I don't use all of its features. But the thing I like the most is it gives me the compile time checks on the SQL that I write. So if I have some insert statement in my application, and it's just written in raw SQL, I can rest assured that if I have some struct that I'm trying to serialize and insert into a row, if the types on my struct are not in compliance with the table, SQLx will give me a compile error. Yeah, I love SQLx. It's like an ORM, but better. So what I like about ORMs is that they give me this really nice interface between my application and the types in the database. So if I have some struct has attributes on it and those are typed, an ORM would be there's this connection between this object and the table or many tables. But I actually really like to write SQL, and a lot of times I end up with SQL statements that don't really fit in ORM super well. So I end up with this code base with some SQL and some ORMs, and it gets really messy. But with SQLx, I can just always write SQL, and I love that as a developer because I enjoy writing SQL. But I still get these type checks because SQLx will look at my SQL statements and then check in the database, does the SQL statement and what you're trying to insert or what you're trying to read and deserialize into some struct, like, is it going to work? Do the types match up? And that is huge. It could be a little frustrating at first until you kind of get the hang of it, but that piece right there is kind of what hooked me on SQLx.
Now, I would guess the other important part is async support, because all of these operations are I/O bound, and you kind of don't want to block the client for concurrent queries. What did you end up using for async, and was it straightforward to integrate into the existing code?
Rewind way back to when we were like first started building in Rust, and it was like, okay, so for async, we kind of have to handle this ourselves. And there's a ton of complexity around that like, frankly, we like didn't want to spend our time like trying to implement. And so then there's a few different runtimes out there, and Tokyo was like clearly the one that was the most popular, the most supported, biggest community around. So we just use that. And, to this day, like when I'm building in Rust, I don't really think about which async runtime to go with. I just use Tokyo.
Right, but what about very complex things like supporting transactions? And by transaction, I mean multiple statements that are executed atomically on Postgres. If you wanted to do that in an async way, I would be afraid that it would get really complex.
Yeah, I don't exactly know how you would, if you had like two separate threads and you wanted to span some transaction across those. I don't know. I haven't actually tried that, so I don't know how it would work. But kind of the way that we implemented I think earlier I mentioned you can bring your own connection pool or really your own executor as long as it has certain traits implemented on it, which is basically, we inherit that from SQLx. But you can start a transaction, do whatever SQL you want. You could go do that with your own ORM. And then you have your like connection or your transaction object that you've created. And if you pass that into PGMQ, then you could go do the PGMQ things through the PGMQ API, and then finally commit your transaction however you want to yourself. So like we lean on Tokyo, we lean on SQLx for that. But yeah, the question about like to do that across threads, that could get tricky to like pass that connection across threads. I don't know how you would do that. It might be possible.
You could probably share the connections across threads with something like argmutext, and SQLx allows that kind of pattern. But at the same time, why would you? Because Postgres already handles that with transactions, and that guarantees atomicity. So maybe you just leave it as an implementation detail to the database?
Yeah, from Postgres side, it's the feature, transactions. We don't have to reinvent the wheel on that part.
Some people might hear this and think, why do I need PGMQ? I can just write my own abstraction on top of Postgres. How hard can it be? It can only be a couple lines of code, right? And we touched on transaction support and edge cases, but maybe you can allude to a few more things that you probably don't want to do yourself. Things that people tend to forget when they build their own abstractions.
Yeah, I mean, with all this stuff, it's just code. So you can always just go write the code. There's these operations that you need to do if you're going to build a queue. You need to have a way to create a queue. So how do you define what a queue is? You can think through that and make it what you want. We have a function called create queue that does it a way that we think is right, and there's an API around it. Sending a message to a queue, it's basically just an insert statement, but that insert is handled for you. And if you're working in Rust, you have some message, and that message becomes like an attribute, in a column on a table. So you need to serialize that message and get it inserted into the table. So if you're using the Rust client, there's some helpers there to do the serialization for you. So, you save a lot of time by, having this stuff like it's already built, it's already tested. You don't have to rewrite a bunch of things. But, I'm sure there's cases out there where somebody, like, it makes sense for somebody to write their own.
Even if you ask me to design a message queue table schema, I'd probably miss something important. I'd add a timestamp, maybe a byte array for the message, though I'm not sure if you support bytes or just UTF-8 strings. Then some kind of locking or ownership field to prevent reading the same message twice. What actually goes into that table?
Yeah, I mean, you're pretty close there. There's a concept that, we're inspired from the SQLx simple queue service from AWS, the visibility timeout, which is kind of that locking feature a little bit. So when you read a message from a queue, you have to specify how long do you want that message to be unavailable to yourself, or if you were to try to read again, or to any other consumers of that queue. So let's say you have like 10 threads all reading from the same queue. That the first time the message is read, you could set it to say, hey, make this message invisible for 5 minutes. And then during that 5 minutes, any of those other threads, none of them will be able to get that exact same message until that message, that time, the visibility time, expires, and then that message becomes visible again. So that piece, I think it's super cool because without that, you would have to have some additional worker process that would watch the queue and look for messages that need to be flipped back available again. But in this way, it's like completely stateless. Everything is just, there's nothing that can really break there. There's no process that crashes and all of a sudden, messages get stuck. They just automatically become visible again.
That's clever. It's sort of a lock-free algorithm because you just update the timestamp when you read it, and everyone knows the message is in flight.
Yeah. The most complicated part of PGMQ is the read statement. It is a super complicated query. It's a for update statement, so it's reading, but it's updating the how many times it's been read. So there's like a counter on that table that keeps track of how many times this message has been read. There's that visibility time, which it's some time that anything after that time that message can be read. Yeah, so there's, when you read the message, it's an update statement to the table, and it's a select for update, which actually creates a lock on that table, and that makes it so that like if 2 threads read at the exact same time, Postgres would figure out, hey, who gets this record first. So the for update just guarantees that only one worker can get the message. But that does create a lock on the table. So you have to, we say for update, that creates the lock. And then there's another clause in there, skip locked, which means any records that are locked, skip over them and go to the next one. And that makes it so that any other workers that are reading aren't sitting there waiting for that lock to leave. They can skip it and go to the next message. And so that lock is pretty quick. That lock only lasts for the duration of, that transaction, which is pretty quick. And like the long-term locking is handled by the visibility timeout.
You probably came up with that on the first try, right?
No, I mean, there's a ton of resources out there. If you just search, message queue Postgres, there's a lot of people have written about for update and skipped locked. It's kind of the standard.
But still, you can make a lot of mistakes when implementing that. And also, you might not know about this research in the first place. You might just naively implement it and do it the wrong way.
Yeah, definitely. Like, if you don't have the skipped lock on there, you could be like, you have 10 threads reading, one of them got a message and the other 10 are just sitting there. They would just sit there forever, until that initial lock was released. So yeah, you could mess it up.
I really like these implementation details. That's what I live for, because That could really hamper your performance. And in the worst case, you don't realize until you're under load. And when you really need it the most, it will kind of fail on you.
Yeah. Yeah, that's a good, I'm glad you mentioned that, because that's kind of a reason why to use something that's been prepackaged, because you can, there's a lot now today, there's quite a few people using PGMQ, and, when people run into issues, like issue gets created on the project, and then, we or somebody in the community resolves it. But there's ways that, try to build your own queue, like there's ways it can go wrong. So, PGMQ as a project has kind of started to be this like place that people go to learn and just use the code of, when they want to do a queue on Postgres, they can, look at that project and either use the code or modify it and do it their own way.
That's why I love open source in the first place, because so much is out there and you can look at the actual implementation and then decide if you really want to go down that rabbit hole and implement it yourself, because just sending in a pull request will fix a problem for every instance out there that has the latest version, of course, which is so great.
Yeah.
How hard would it be to abstract that to other databases? For example, if there was a customer that needed MariaDB support or MySQL support, how hard would that be if you had to support that?
I guess, it would be, there's some SQL files in the PGMQ project, and it would be like, hey, for every one of these statements, what's the equivalent in the other database? And if you translated that, then it, theoretically should work.
The cool thing is that you could use Rust's feature flags. So the project builds against the database that it depends on. I was wondering about Postgres listen and notify support. Where do you draw the line between using native PubSub versus needing a full message queue?
We've had some discussions of using those features from Postgres in PGMQ, but I don't think they are exactly, like, you couldn't just replace PGMQ with alert and notify. Well, mostly because, if you're going to send the message across one of those notification channels, like if that message doesn't make it, then it's kind of gone, and you have no record of it. In PGMQ, it's every message is a row in a table, and you can archive that row or just completely delete it if you want. So you still have like a complete audit log of every message if you want it. If we were just to move it into one of those other channels, and it's kind of gone, unless we build something to handle it. But I do think it would be really useful to use it as a way to notify consumers that there are messages available in a queue. So right now, if your application is reading messages from a queue, you have to pull the queue, pull it once every second, or have some back off logic, pull it every second and then back off to 10 seconds or something. But it would be nice to be able to subscribe to the queue and have one of those notifications come to you and say, hey, there are messages now pull. And that could, really help some efficiency if you have really low latency requirements and, you can't wait. A 1 second pull interval is too long and you need to know right away, that, and you don't want to just pull every 10 milliseconds or something less. If we had something implemented on those features, it could help a lot, I think.
Also, on top of this, you could use the Tokyo stream abstraction, and you could just iterate over the messages, and the futures would resolve as quickly as messages come in. And it would all kind of beautifully happen under the hood, where you say, well, you get a future ready and it contains the value, and that is your message. And I guess it would be kind of nice to have that. How far away are you from that reality?
Well, I think we would first need to get the, implement a way to like set up those channels on any given queue. And I don't think that would be super difficult. There's probably a way that this could all be implemented purely on the Rust client side too. So like if I think of how like librd Kafka reads messages from a Kafka topic, it pulls, but it is pulling messages in batch to the client. And then the consumer of librd Kafka, iterates over those messages. And we could probably do something similar in the Rust client, where you have some pull interval, but we're handling that pull asynchronously and pulling messages back in batch. And then your Rust application, could iterate over those messages asynchronously if it wanted to. I always really liked how libRD Kafka did it, because as a user there, all that stuff is abstracted from you, but it's super efficient because it is pulling for you. And unless you really get into the weeds, you don't really know that it's pulling, and it's pulling messages in batch. But we could probably do the exact same thing in the Rust client.
What's your biggest deployment at the moment?
So I think I mentioned earlier this architecture with a control plane and a data plane. We have several data planes. There's a data plane in AWS, Azure, Google Cloud, and then some self-hosted ones as well. But all those public clouds, they all read messages from a single Postgres instances, and there's multiple queues within that. And I think at peak, there's like 10,000, 10,000 per minute, maybe 5 minutes or something. But really, like, the scalability of that, it's all comes down to what can Postgres handle. How many inserts, how many updates per second can Postgres handle? Because that's really all that PGMQ is doing, is inserts and updates. Well, inserts, updates, and deletes.
Okay, so if you use that for a larger deployment, it certainly won't be the bottleneck in your application, unless you are at web scale, and then you always have bigger problems. You have bigger fish to fry. Okay.
Yeah.
What's your setup for the production cluster right now?
It's a dedicated Postgres cluster for the queue. Yeah, and it's those specs on it are exactly right. Yeah, and it like never really gets over 20% CPU or memory. Memory utilization is kind of just hovers around 25%, probably because that's what shared buffers are set to on that thing. But it is dedicated to the queue, so I think it is over provisioned.
Well, that's at least better than being under provisioned. What are some of the other use cases of Postgres that you see in production a lot?
Yeah, full text search is built into Postgres. So if you're trying to do that, like, it's pretty easy to get up and running. We also have a number of people using our VectorDB stack, which that's primarily PG Vector, which is another open source project out there that lets you kind of gives you the data type of a vector, and then the operations to do similarity search on top of it. It is definitely the gold standard for working with embeddings within Postgres. And then we built kind of a wrapper extension around it using PGRX and Rust. It lets you, say you have a table with some text in it, and you want to generate embeddings from every row in that table. Be like, hey, I have this table. I want to use OpenAI, or I want to use Anthropic, or I have a self-hosted model, and I just want to get embeddings for this table. So our wrapper extension, it's called PG Vectorize. You just call a function on a table, tell it which model you want to use, and then in the background, it's using PGMQ to look at the table and be like, hey, which columns do we need to get embeddings for? Pull that data, call the transformer model, get the embeddings, and insert those embeddings to another table or the same table. It's configurable, but yeah, it's kind of like helps you with the orchestration there.
I like that you use your extensions in combination with other extensions and calling into them. It's kind of cool. How do you ensure safety between the boundary of Rust and Postgres?
That Vectorize extension, it runs in a background process that Postgres manages, and we purposely don't use the SPI, that interface previously, because it's kind of unnecessary. So we just use SQLx. So Postgres spins up this background process that reads from that queue of jobs that it needs to create embeddings for, and we just use SQLx for it. So it's kind of treated as just like a normal application internally. So there is no like interacting with FFI or anything going on there. We treat it as just after Postgres starts it, then it's like normal Rust application. Since we built it that way, we have the option on our cloud platform to run that background worker in a separate container. So instead of as a Postgres background worker, we just take that same Rust binary and run it in a separate container next to Postgres. So that's an even better way to get around that limitation of like memory management. Well, if it's not even on the same host as Postgres, then you can scale that thing independently.
With Tembo, you shipped your first real Rust production application. What took you the longest to wrap your head around in Rust?
Yeah, so today I love working in Rust. It is a joy to build software using Rust. But when I was getting started, there was this huge hump, this hill to get over. And it was super frustrating early on. One of those things was just wrapping my head around like null. There is no null. You have like some and none. And I looked at that and I'm like, this is so weird. I came from Python, so you had a none type, but it was not an enum. And until I like learned that it's an enum with like data is what how Rust handles null values. So it's this like wrapper around your data, and is it null or is it not? That was, I don't know why, but it was really hard for me to grasp that. And in that same like direction, error handling, where it's like okay or error, I don't know why it just took me so long to wrap my head around. Like, yeah, you basically wrap your data. If you have a function and it could error, well, you wrap it in this thing, a result, and it's an enum. And it's the same for none, or like how Rust handles none. And I don't know. I think like not today. I love those things. It just makes it so clean. Like, is there an error or not? Did it return something or was it there nothing? It's super clean when I look at it today. But when I was learning Rust, I'm like, what is this? This I don't even understand. So I don't know what would have like made it easier for me to learn that early on, but I remember it being super frustrating. And then all of a sudden I got it. I'm like, oh, this is awesome. I love it.
How long did it take you until you had a good grasp on the language?
I'd say so. When I started, I was learning full time basically when I was learning Rust, and I think it was 2 months. Maybe that's slow for some people. Like all day, 5 days a week at least. I was able to get up and like be building software and still not quite understanding error handling and none, handling of none types. So, but yeah, I think it was 2 months for me of pain.
2 months of pain. I really like that framing.
But the one thing I loved like day one though was having cargo. Like, I came from Python and it was like, how do I get my environment set up to run my application? And at the time it was like, do I use virtualenv? Do I use Poetry? Do I just install everything with pip? It's a mess. Like, there's some projects that are making it better in Python today. Like UV is doing a really great job solving that problem. But when I was learning Rust, it was like, hey, how do I run this? How do I run this application? Oh, cargo run. That's it. How do I test it? Cargo test. It was just so intuitive. How do I add a library from crates? Cargo add. And it was just all built into the tool chain. And I didn't have to go search and read a bunch of blogs to figure out how to just get started. So that from day one was probably what kept me there through those 2 months of pain.
Oh yeah, day one in Python is strange because on one side the language is great, but on the other side the tooling is not so great. And you really get those mixed feelings. On that note, shout out to Charlie Marsh from Astro, who was a guest in episode 3 of season 4. You might want to check out that one. So they do great work, but the experience before that was subpar. The tooling was a bit all over the place and very difficult to use.
Yeah, I have like nightmares of. So when I was working at Shipped, all of a sudden they started issuing employees the MacBooks with Apple Silicon. So they all had ARM architecture. And all of not every project out there had Python wheels for ARM. So now, like, all of a sudden, new employees coming in, like, their local environments would just not work with our internal libraries because we weren't building wheels for ARM. Like, we were using Kafka, and libart, or Python's Kafka library, didn't have a wheel for ARM for the longest time. It was like, okay, we have to compile this stuff from source all of a sudden. And it was, I had nightmares from that. It was like everything fell apart.
Well, at least they did a great job on the migration from Python 2 to 3. That was extremely painless, of course.
Yeah.
Just kidding. It was a nightmare.
Yeah. The most obvious one there is just like trying to print something. It's like the print API changed, you know?
Yeah, thanks for bringing back that memory. By the way, do you have to touch a lot of Python nowadays?
Not too much. You know, there's a lot of stuff in machine learning is still, you know, there's lots of libraries out there for machine learning things in Python. And in the machine learning space, Python's mostly used as a wrapper around some C library that's super well optimized. Rust is, I'd say, catching up, and like Hugging Face has built some Rust libraries that kind of do the same thing as the Python equivalents. So, but yeah, most of the time, I mean, if I'm building a web server today, I'll just grab Actix and run with it. You know, if I'm working with data in Postgres, I'm going to grab SQLx. 10 years ago, it would have been like Flask or Fast API, or maybe not 10 years ago for Fast API, but, you know, I have the equivalent of everything that I would, you know, 5 years ago would have gone to something in Python. I have, you know, for me, I'd just pick Rust. It's just easier. It's a better experience.
And on that very positive note,
yeah,
what's your final message to the Rust community?
Yeah. I mean, keep contributing to the project. Like, the project doesn't live unless people are working on it and making it better. You know, today, now that there's really no such thing as finished software or a finished programming language. It's not like software is distributed in the mail where you burn stuff to a disk and mail it out, and it just runs that way forever. Software is living, breathing organisms now. So things have to be constantly fed. And for Rust, like, if people stop contributing to Rust, and, you know, like, the project won't go on. So I guess my biggest message would be thank you for building awesome stuff, and please keep doing it.
Adam, thanks a lot for the interview.
Yeah, thank you.
Rust in Production is a podcast by Corrode. It is hosted by me, Matthias Endler, and produced by Simon Brüggen. For show notes, transcripts, and to learn more about how we can help your company make the most of Rust, visit corrode.dev. Thanks for listening to Rust in Production.